So let's learn calculus in polar coordinates. So let's first talk about area. So if I have r as a function of theta, and I want to find an area like this. So theta is starting at like alpha, so maybe alpha is this angle, and going up to beta, so beta is this angle. And I want to find this area. Okay, here's what we're going to do. We break this area up into a bunch of very small pieces, and then I'm going to approximate the area of each piece. I'm going to add up all the areas of these pieces, and that's going to be my approximation for the area. And of course, since this is calculus, I'm going to do the limit as these pieces get smaller and smaller, and that's going to be the exact area. Okay, so let's do that. First of all, if I draw this, basically each piece, especially if these pieces are very skinny, these pieces are almost the sector of a circle. So a sector of a circle, it's like a slice of pizza, except we're talking about very skinny, like very small angles here. So it's like a skinny slice of pizza. And the area of a sector, the way I remember it is, it's just a fraction of the area of the circle. So if I take the area of the whole circle, that's this much, and then I say, well, I didn't want the whole circle, I just wanted like one fraction of it, and then I say, what fraction? Well, this is an angle of phi out of a possible 2 pi, because the whole circle would be 2 pi. So this is the fraction of the circle that I want, and then I just simplify this. So the pi's cancel, I get 1/2 phi r squared. So that's the formula for the area of a sector of a circle. So what I have here is a bunch of sectors of circles, and so like this one has a different r, and this one has a different r, and this one has a different r. So basically what I'm going to do is I'm going to add up, because I'm adding up all the areas of these sectors, and then here's the area of a sector. I'm using this formula. The angle is what I'm going to call delta theta. So delta theta, that's like a small change in theta. So each one of these has an angle of delta theta. So this phi turned into a delta theta. I've got my 1/2 here, and then this is my r squared, because this is the graph r equals f of theta, so instead of r, I write f of theta. And I add this all up, and of course this is a Riemann sum, so when I do the limit as delta theta goes to 0, so these sectors are getting skinnier and skinnier, this approaches an integral. This is the integral from alpha to beta. Those are my theta values. 1/2 f of theta squared d theta. Or if I like, I can write it this way, because r and f of theta are the same thing. So this is the formula for the area of this shape. Okay, so that's a thing we just learned. So what else do we do in calculus? Of course, one thing we do is slopes of tangent lines, so like dy over dx. So let me give you a formula for that, and I'm going to show the work here. So, whoops, I made a mistake. So the first thing we're going to do is treat this like parametric equations, because one way of viewing polar coordinates is just a specific form of parametric equation. And what do we do in parametric equations? If I want dy over dx, I do dy over dt and then dx over dt, except instead of t's, we have thetas. So the mistake that I made was writing a t down here. These should both be thetas. I got the theta up there, I just wrote t down there, so I just fixed it. Okay, and recall that y is r sine theta and x is r cosine theta. So when I do dy over d theta, that's the derivative with respect to theta of y, which is this, And dx over d theta is the derivative with respect to theta of x, which is this. And we can do that. So remember the product rule. And keep in mind that r is a function of theta. So the derivative of r is, we could say r prime or dr over d theta. So here I go. Let's do the product rule. So for the product rule, I do the derivative of this, which is dr over d theta, times this, plus this, times the derivative of this. Okay? And now let's do this one. So I do the derivative of r, and then derivative of this is negative sine, or wait, sorry. I leave this alone. I do the derivative of this and then leave this alone. Yes, okay. Plus, now I'll do this and do the, and yeah. I'm messing up a lot as I speak, but there we go. So I left the r alone and did the derivative of cosine. So, okay. I'm almost too lazy to do this, but let me just rewrite this, and all I'm doing is I'm putting this negative in front. So this is a formula for dy over dx if you need to find the slope of a tangent line of a curve that's given in polar coordinates. Okay. Let's derive one more thing. One thing we've been doing a lot of lately is arc length. And I'm going to sort of derive this the same way I derived the last one. I'm going to take a known formula that's valid for parametric equations. This is, we were used to seeing this where all the thetas were replaced with t's when we were doing parametric equations. But I just wrote it with thetas in there. So this is going to be our starting point. Or actually, okay. The next line is going to take a fair bit of space. So let me just start a new line here. I'm actually going to take some of the work that we already did. Because when we were doing the last thing we did, we found dy over d theta and dx over d theta, and I'm about to use those things again. So when we did dx over d theta, we got this, which is the same as this. So dx over d theta is that. So I wrote that there. dy over d theta is the top of this fraction. So I'm going to copy this down here. Okay. Let's square this out. So I've got this squared, dr over d theta squared cosine squared theta. I'm going to have a minus 2 times this, so minus 2 r dr d theta sine theta cosine theta, plus this squared. Okay, let's find out if I have space to square this out. I'm going to have this squared, so dr over d theta squared. sine squared theta. I'm going to have 2 times this. So 2 dr over d theta r sine theta cosine theta. And then, yeah, forgive me, but I'm just going to sneak this last term in there. It's just an r squared cosine squared theta, and then a d theta at the very end. Now let's look carefully, because this is going to simplify quite a bit. I have this and this, which are the exact same thing, and one of them's negative and one's positive, so they just go away. Okay, now I'm going to have some sine squared plus cosine squared going on. So let me try to be careful about how I find those. I've got an r squared sine squared theta and an r squared cosine squared theta. And if I pull out the r squared, then I'm just going to have 1. Because if I pull out the r squared, then I have sine squared plus cosine squared, which is just 1. So I can just write r squared, and that takes care of this and also this. So these 2 purple underlined things are now taken care of. Let me use a different style of underlining, because I've got this, which I will double underline. So that's like derivative of r squared cosine squared. And then I've got derivative of r squared sine squared. So I can pull dr over d theta squared out of this, and then I'm just going to have 1, because if I pull that out, then I'm going to have a cosine squared plus sine squared. In other words, I've just got that. And that's everything. So like I said, that simplified quite a bit. And this is our formula for arc length in polar coordinates. Okay, so let's just do a quick example just using one of these things. So we'll find the area of this. So we're just given a graph. We are given a formula like what function r is of theta, and then this is the shaded region. So this is the formula that we derived. I'm just going to look at the picture to figure out my alpha and beta. These are the theta values. So theta goes from here, which is pi over 2, to here, which is pi. 1/2. Here's our d theta. So now we just have to do this integral. Okay, so I can pull the 1/2 out. Let's square this. So 4 plus 4 cosine theta plus cosine squared theta. All right, so let's take inventory here. Integrating this is going to be easy. This is just going to be 4 theta. This is just going to be a 4 sine theta, no problems here. This is a little bit of a pain. We know what to do, but this takes a little bit of work. Cosine squared, what we have to do is we have to do that half angle identity. Cosine squared is the same as like that. So actually, okay. Let me just collect like terms. This is kind of a little thing, but I've got a 4 here and a half here, so that's 9 halves. Okay. Let's integrate everything. 9 halves theta plus 4 sine theta plus, okay, I've got 1/2 that's already there, and then the antiderivative of cosine 2 theta is a 1/2 sine 2 theta. Okay. So let's plug in pi. 9 pi over 2. Sine of pi is 0. Sine of 2 pi is also 0. Okay, let's plug in pi over 2. Sine of pi over 2 is the y-coordinate of this point, which is 1. When I plug in pi over 2 here, this would be sine of pi, which is 0. Okay. So I've got 9 pi over 4 minus 9 pi over 8 minus 2. So I can get a common denominator here. So this is going to be 18 pi over 8. So I get 9 pi over 8 minus 2. Okay. So as usual, I mean, integrating something can take some work, but this is an easy formula to use. Like we're done using the formula once we get here. All the rest of this work is just dealing with whatever we have to deal with to find the antiderivative, which can take some work, but it's an easy formula to use.